In the 1970s, astronomers discovered that our Milky Way galaxy is moving. Drawn by great invisible forces, we were being pulled towards something, but we couldn't see what. Our final destination was hidden by the zone of avoidance, a region of the sky obscured by the gas and dust of the galactic disk. Like a tiny raft adrift in a vast ocean on a moonless night, we were caught up in the current, heading towards who knows where. And we weren't alone, for it wasn't just the Milky Way that was in motion, but all of our neighbours. Two astronomers, R. Brent Tully and J. Richard Fisher, were using the Parkes Radio Telescope in Australia to conduct a survey of distant galaxies, attempting, with their meagre observations, to reconstruct their movements. Around the same time, multiple teams of astronomers were observing the cosmic microwave background, the bath of radiation that survives as a relic from the early days of the Big Bang. Independently, both groups found the first hints of this great cosmic flow. The galaxies that Tully and Fisher mapped seemed to share a common locus, their reconstructed velocities all roughly pointing in the same direction. As for the cosmic microwave background, its temperature across the sky revealed a bias. It was slightly hotter in one direction and slightly cooler in the other. Much of this discrepancy could be eliminated by considering the motion of the Sun around the core of the Milky Way, but after that subtraction, a residue remained, an unexplained source of motion relative to the ultimate cosmic reference frame, a speed amounting to hundreds of kilometers per second. It appeared as if the Milky Way and all the other galaxies in our nearby vicinity of the cosmos were being drawn to a particular spot, a specific location in the universe, as if tied by great invisible chains stretching tens of millions of light years. We couldn't see it, couldn't map it, couldn't figure out what it was. For decades, the best we could do was simply name it, the Great Attractor. A great source of inexorable motion, a persistent sink of gravity, a single point in the cosmos that pulls and pulls and pulls. Our entire galaxy and thousands of others, home to hundreds of billions of stars and countless planets, drawn to the Great Attractor like a helpless moth to a flame. And yet, no matter how odd this may seem, this is not an unusual situation in the cosmos. For the universe is far from static. Every object within the universe is in a state of restless motion. From the orbit of the Earth around the Sun, to the Sun's drift within our galaxy, to the hurtling of the Milky Way towards the Great Attractor. And that is not even the largest example in the universe. For the Great Attractor turned out to be just the tip of a far larger cosmic iceberg flowing across the sky, vast cosmic structures and motions dwarfing anything we had ever seen before. And so nothing is still. Everything is going somewhere. The question is, where? On September 23, 1999, the Mars Climate Orbiter lost contact with NASA as it approached the planet. The mission was totally lost, and it later turned out to have been down to a mistake converting metric to imperial units. Even multi-billion-pound projects that are supposed to work seamlessly can fail. Our universe is defined by motion, and one way to describe the history of science is through our increasing awareness of the restlessness of the cosmos. For millennia, the brightest scientific minds in Europe and the Middle East believed that the Earth was perfectly still and that the heavens revolved around it. Those early astronomers busied themselves with attempts to explain and predict the motion of other objects, the Sun, the Moon, each of the known planets and the stars. And their predictions worked surprisingly well. But their cosmological system of motion wasn't perfect. In fact, it was an ungainly mathematical mess, relying on small circular orbits nested within larger ones, with some centered on the Earth and some centered on other points. And so, on his deathbed in 1543, the Polish astronomer Nicholas Copernicus published a radical reformulation of the old system that put the Sun at the center of the universe, still and motionless, with the Earth set in motion around it, along with all the other planets. The reaction to the work of Copernicus was mixed. On one hand, it was a bold reshaping of the universe. On the other, It was arguably just as messy as the ancient system it was trying to replace. And on top of this, it introduced more than a few questions that had no easy answer. First and foremost, if the Earth was moving, how could we tell? We know we are moving on the surface of the Earth through a variety of ways. We can feel the wind against our face when we run or watch as a distant goal draws nearer. So why don't we feel a great rush of wind as the Earth orbits around the Sun? Or why aren't we flung off into the void of space due to the incredible rotation of our planet? It took centuries of science and the development of Newton's theory of gravity for the full picture to come together. Today we know that we don't feel the motion of the Earth because we are in motion along with it. And since the vacuum of space is just that, a vacuum, there's nothing for us to push against and betray that motion. But how can we guarantee that the Earth truly is in motion? Is there a standard reference? Indeed, Newton assumed that such a standard existed, that there was a fixed frame of universal reference from which all motion could be measured. In crafting relativity, Einstein rejected the concept of a fixed, universal ruler against which we could judge motion. Instead, all inertial motion was relative. The only way to measure your motion is in reference to something else. From this fundamental idea, the rest of relativity blossoms, the fabric of space-time, the equivalence of mass and energy, and limitations of the speed of light. All of it. Imagine cruising in an unpowered rocket ship and encountering your friend doing the same. You are both in an inertial frame of reference, moving at a fixed speed. As you cross paths, you may declare that you are moving and that they are staying put. In relativity, they have just as equal a right to state that they are moving and that you are the one who is standing still. These two perspectives are equally valid. Despite this, we can tell that the Earth is spinning because of the Coriolis force, which twists air streams around to form hurricanes and typhoons. Even if our skies were completely blank, with not a single star to be seen, with nothing left to measure except what we have right in front of us, we could still deduce the motion of the Earth's rotation. But the movement of the Earth throughout the greater universe is another matter. For that, we need to identify another frame of reference, another yardstick for measurement. Otherwise, we could rightfully claim, just like any other object in the universe, that we are motionless and that the rest of the cosmos, every planet and star and galaxy, moves around us. Thankfully, the universe itself provides the tool we need. We don't live in a static universe, but an expanding one. The cosmos changes from day to day. In the past it was smaller, and in the future it will be larger. This allows us to write down a preferred frame of reference, one that expands with the universe, enabling us to measure motion relative to that. In other words, at large scales, the universe is expanding. On average, galaxies are getting farther away from each other with time. Motion can then be defined as anything deviating from this general outward flow, termed peculiar velocity, which can range from a few hundred to a few thousand kilometers per second. With this framework, cosmologists can comprehend not just the Earth's rotation or the planet's orbit around the Sun, but also the movement of the solar system within the galaxy and the actions of the Milky Way in the wider universe. Without feeling it, without taking a single step, you move an incredible distance through your life. First, there is the Earth's rotation. Depending on where you sit on the globe, you could be spinning at up to 1,600 kilometers per hour. For most people who live in mid-latitudes between the poles and the equator, the typical everyday velocity is around 1,000 kilometers per hour. Over a typical human lifetime of around 80 years or 700,000 hours, this adds up to about 1 billion kilometers due to the Earth's rotation. The Earth also orbits the Sun at an average speed of 30 kilometers per second. This movement accumulates to around another 80 billion kilometers over your lifetime, although it follows a rough circle, so it doesn't mean you're going anywhere relative to the Sun. Beyond this, the Sun and all the planets, comets and asteroids in the solar system orbit the center of the Milky Way galaxy. This journey takes 230 million years to complete a single orbit, with an average speed of 230 kilometers per second. This speed provides profound evidence for dark matter within the galaxy. When calculating the mass of all the observable stars and gas, it's insufficient to keep the Sun in orbit. Without an additional source of mass, the Sun would have been ejected from the Milky Way billions of years ago. The missing mass is attributed to dark matter, an invisible substance that holds the galaxy together. Besides orbiting the galactic center, the Sun also bobs up and down through the galactic plane due to gravitational interactions with its neighbors. Over millions of years, this motion sees the Sun rise thousands of light years above the plane before plunging back through it. Currently, the Sun is passing through a region known as the local bubble, created by a supernova explosion millions of years ago. The bubble's density is less than 1/10 the average density of the Milky Way, so low that it would be considered a vacuum in a laboratory on Earth. Our solar system entered this bubble between 5 and 10 million years ago and will traverse its 1,000 light-year span for millions of years to come. But this is far from the end. Against the backdrop of the expanding universe, the Milky Way is moving toward our nearest galactic neighbor, the Andromeda Galaxy. In the far future, our night sky will be unrecognizable. The moon will appear smaller, fainter and more distant. The Sun will be larger and brighter. The constellations we know will be replaced by new stars in our cosmic neighborhood, and Andromeda will dominate the sky, filling it almost completely. Andromeda's appearance will be distorted and twisted by the gravitational forces at play as it merges with the Milky Way. A billion years after the collision begins, Andromeda will be ablaze with new star formation, producing stars at a rate 1,000 times faster than now. Eventually, long after the Sun has exhausted its nuclear fuel and become a white dwarf, the merger between Andromeda and the Milky Way will be complete. The resulting galaxy's core will glow brightly, eclipsing any other object in the night sky. Over time, the giant stars will burn out, ending in supernova explosions. If Earth survives these events, it will face a sky slowly dimming into darkness as the last of the visible stars vanish. In the 1920s, Edwin Hubble discovered that the Andromeda Nebula was actually a separate galaxy, an island universe 2.5 million light-years away, more than 10 times further than any previously hypothesized object. Measuring Andromeda's speed was not easy due to its size. Telescopes could only capture parts of it, showing varying velocities. It took until 1957 for Dutch astronomer Hendrik C. van der Hulst to provide a solid measurement using 21-centimeter radiation from neutral hydrogen. His careful radio observations revealed a redshift indicating that Andromeda was moving toward us at an average speed of about 296 kilometers per second, with an uncertainty of around 10 kilometers per second. Throughout the universe, astronomers see countless galaxies caught in the act in a variety of stages and interactions. There are galaxies colliding head-on and others just glancing by each other. Sometimes they are perpendicular, and sometimes they are slamming their spiral arms against each other. Sometimes more than two are caught in a struggle for gravitational dominance. And so the process of galaxy mergers began billions of years ago, even before the galaxies themselves arose, and it will continue into the future. For the journey of the Milky Way does not end at its merger with Andromeda. Our motion through the universe is far from over, and it's towards a direction that we barely understand. Sometimes, mathematics can be a crystal ball that lets the careful observer peer through the distant reaches of space and time. And sometimes, That crystal ball begins its own story in a space and time far, far removed from modern-day cosmology. Take the wide-reaching consequences of the work of the French mathematician Gaspard Monge, although he didn't know it at the time. Instead, as Minister of the Marine in revolutionary France in 1792, he was more interested in working out optimization problems in the transportation of goods. Several decades later, the great pioneer André-Marie Ampère took Monge's work and expanded on it, generating an equation that has since found use in a variety of economic settings. For example, in figuring out the most efficient way to move resources between mines and factories. And in the midst of World War II, the Soviet mathematician Leonid Kantorovich took the work of Monge and Ampère to the next level, extending and applying their equations to the thorny logistical problems faced by the Soviet war machine. But finally, in a beautiful example of the universality of physics, in the 1970s, Canadian-American cosmologist Jim Peebles realized that the same equations could be used to describe the efficient movement of mass in the assembly and formation of galaxies. Coming from a humble background, the son of a grain exchange worker and a homemaker, Jim would go on to study at Princeton University and eventually become a giant in the field of cosmology. Though in the early days of his research in the 1960s, cosmology was not widely considered a serious field of study. We knew that the universe was expanding and that the Big Bang picture was likely correct, but there was so little observational data available that most astronomers considered the field a dead end, with no serious future. But instead, Jim pushed on and pioneered almost every aspect of modern physical cosmology, from the growth of structure to the earliest moments of the Big Bang, work that would earn him a Nobel Prize in Physics in 2019. And completing the circle, it was two astronomers, the French Roya Mohayyai and the Russian Andrei Sobolevsky, who followed up on Jim's pioneering work and finally turned the so-called Monge-Ampère-Kantorovich equations into a cosmological crystal ball. They found that they could take the present-day positions of galaxies and combine that information with limited information of their velocities to transport those galaxies back in time. The trick behind the approach is that we know how galaxies move. They are influenced by their mutual gravitational attraction, and we know how gravity works. So this technique allows cosmologists to take the current state of a collection of galaxies and compute where they should have been in the past. It's not a perfect technique by any means. Every step backward in time introduces ever larger uncertainties, and the technique can't go all the way back to the Big Bang, but it does work. With this method, Brent Tully and collaborators have released continuously updated catalogues called Cosmic Flows, which map out tens of thousands of galaxies around the Milky Way, along with their positions billions of years ago. That information allows him and his colleagues to reconstruct the motions of galaxies through cosmic time, not just into the past but into the future, giving them the ability to predict where the Milky Way is headed. Our portrait of the Great Attractor is hazy at best because it lies within the zone of avoidance, the direction in the universe obscured by our own galaxy's dust. But some wavelengths of light can penetrate that dust, and surveys taken with radio, infrared and X-ray have shown us glimpses of what lays beyond the veil and what might be sitting within the Great Attractor's region. As best we can tell, the heart of Laniakea, the focal point for the Great Migration of 100,000 galaxies, including the Milky Way, is the Norma cluster, named for the constellation we must peer through to see it. It is several times larger than a typical galaxy cluster and sits about 220 million light-years away from us. And so, even at a speed of over 100 kilometers per second, the Norma cluster is so far away that our journey towards it would take over 100 billion years. But it happened to sit at the bottom of an immense gravitational well, the singular point of attraction for this entire local region of the universe. Over time, Norma will only grow more immense, and it continues to collect more material within it. But recent surveys, again using the Monge-Ampère-Kantorowicz reconstruction technique, have revealed that our motion towards the great attractor, that is, the Norma cluster, is not the end of the story. For one, even though our understanding of Norma is vague at best, it appears to be a little too small. There seems to be an additional source of attraction sitting even further beyond the Norma cluster, for Norma too appears to be in motion. The structure was first observed by Harlow Shapley of the Harvard College Observatory in 1930, who could only dimly perceive a distant nebulosity. The incredible mass of the Shapley supercluster is influencing every galaxy, every group, and every cluster around it for hundreds of millions of light years. If we were to give the universe enough time, and for all this motion to continue unabated, then Laniakea would transform into a single compact object, a much more immense version of the Norma cluster that currently sits at its heart. And that object would eventually make its way to a similar one situated at the center of the Shapley supercluster. And there are even hints of additional motion on even greater scales. In 2008, NASA astronomer Alexander Kashlinsky was observing a subtle signal found in the cosmic microwave background. Known as the kinematic Sunyaev-Zeldovich effect, it's a tiny imprint caused when light from the CMB passes through a galaxy cluster on its way towards us. By comparing these signals in different regions of the sky, Kashlinsky found that there appeared to be a large flow of clusters towards a direction on our sky between the constellations Centaurus and Vela. The universe is vast and filled with countless wonders. From the smallest particles to the largest galaxies, everything is interconnected in a cosmic dance. In this chapter, we will explore the grand structures that make up our universe, from stars to superclusters. The Milky Way started out small, just a few thousand stars huddled together in the dark, but it was birthed in movement and through successive mergers amassed itself to its present-day status. The same story has played out trillions of times across the visible universe, creating galaxy after galaxy. This is the story of hierarchical structure formation, how our universe built itself like a towering Lego masterpiece, brick by solitary brick. There are hierarchies of structure in the universe: galaxies, groups, clusters, and superclusters. And along with that hierarchy of structure comes a hierarchy of movement. The galaxies are already assembled from countless mergers in the past. Groups, like the local group that contains the Milky Way, Andromeda, Triangulum, and a host of smaller dwarf galaxies, are still in the process of collapse and merger. Roughly 100 billion years after the Milky Way and Andromeda meet each other, the other members of the local group will collapse in with them, forming a single mega-galaxy. The groups of galaxies, like the local group, are in motion as well, trekking along through the expanses of the universe towards their local centers of gravitational attraction, the clusters of galaxies. The nearest cluster to us is the Virgo cluster, already home to thousands of galaxies and drawing tens of thousands more towards it. In addition to the motion of the Milky Way to Andromeda, as a group we are also falling towards Virgo. This process was set in motion during the earliest moments of the Big Bang, but only ramped up a few billion years ago. As clusters like Virgo grew, they exerted more gravitational influence on their surroundings. This pulled more material onto them, which increased their mass and increased their gravity. Long ago, the nascent Virgo cluster started weakly tugging on the local group, And as the cluster grew, that gentle tug turned into a mighty force. This growth through gravity does not stop at the scale of clusters. Clusters are the largest gravitationally bound structures in the universe. They are already formed, already complete, and simply hungry for more. But the clusters themselves participate in yet another level of growth, one that is not quite finished: the building of the superclusters. Superclusters have always had a loose definition in astronomy, usually referring to anything vaguely resembling a coherent structure on scales larger than clusters. As far back as 1863, astronomers William and John Herschel noted an excess number of nebulae, which were really galaxies, in the direction of the Virgo cluster. In the 1950s, the astronomer Gérard de Vaucouleurs tentatively identified this excess of galaxies as a structure in its own right, calling it the local supergalaxy, which he later changed to local supercluster. But because superclusters are not yet fully assembled, they have no easily defined limits or boundaries. Initially, astronomers believed that the Virgo cluster sat at the heart of the local supercluster, also confusingly and uncreatively known as the Virgo supercluster. A rough collection of around 100 galaxy groups and individual clusters spanning over 100 million light-years in breadth. Beginning in 2014, Brent Tully, who first identified the beginnings of the Great Attractor, along with collaborators Hélène Courtois, Yehuda Hoffman and Daniel Pomerede, proposed a new definition of supercluster. This definition was not based on spatial extent, but on movement. They employed the Monge-Ampère-Kantorowicz reconstruction technique to spring their galaxy surveys into life, changing them from static snapshots of the present-day universe into living entities, seeing where these tens of thousands of galaxies near to us came from, and discerning where they're going. And it was the motions of these galaxies that revealed the true extent of our local supercluster. It turned out that what we thought was a supercluster was just a single branch, one of four, of a much larger assemblage, an entity that Tully and collaborators named Laniakea, a Hawaiian word that roughly translates to immense heaven or open skies. The Milky Way galaxy belongs to the local group because we are all moving towards a common center, which will eventually become a gigantic singular galaxy. The local group belongs to the Virgo branch of our supercluster because we are all headed towards the Virgo cluster. And the Virgo supercluster branch belongs to Laniakea because we are all moving towards the center of Laniakea, 100,000 galaxies in total, spanning across over 500 million light-years in length, assembled on four separate branches, each once considered superclusters in their own right, all headed for a single destination: the beating heart of Laniakea, the local center of attraction of this portion of the universe, the final assembly point of a construction process that began billions of years ago and will take hundreds of billions of years to complete, the center of it all. It was perhaps the only time that Einstein didn't trust his own mathematics. Early in his career, he made a name for himself with his leaps of imagination and insight, grounded in a deep understanding of the physical universe and the mathematics needed to bring his ideas to light. Indeed, in a single year, he crafted the special theory of relativity, discovered a foundational principle of quantum mechanics, and conclusively demonstrated the existence of atoms. But in 1917, Einstein tripped over himself. He had just developed general relativity and found numerous applications for it, and so had decided to take his newfound equations and use them to describe the entire universe. After all, gravity is the only force that operates at large scales across all objects, and so the language of general relativity should have been more than capable of describing the evolution of the cosmos. Yet what he found surprised him. His equations naturally predicted a dynamic universe, one that was always in motion, with all objects at large scales either collapsing together or expanding away from each other. This went against the conventional wisdom at the time that while planets may orbit and stars may move here and there, the large-scale universe was fixed and static for all of eternity, and so, for whatever reason, Einstein did not want to disrupt the established order. He found an opportunity in the form of a cosmological constant, a number that he could slip into the equations without breaking them. In the solar system, this cosmological constant did not affect any measurements, but on large scales, it would act to stabilize the universe, overcoming the natural tendency of the objects in the cosmos to move. Unfortunately for this idea, just a few years later, Edwin Hubble would discover the expansion of the universe. While Einstein never admitted it in public or in any letter, his closest friends recalled that Albert would refer to the cosmological constant as his greatest blunder. Yet despite Einstein's regret, the constant never quite went away. There was no need for it to explain any cosmological observations, but there was also no theoretical need to completely kick it to the curb. The great Soviet astrophysicist Yakov Zeldovich recognized its importance when he equated the cosmological constant to the vacuum energy of space-time, just two different expressions of the same fundamental concept. And in 1998, astronomers realized that the expansion of the universe was accelerating. The most likely culprit for this mysterious accelerated expansion, the vacuum energy of space-time. And so, in the span of only a few weeks, cosmologists around the world dusted off their history books and reacquainted themselves with Einstein's greatest blunder, and how that little innocent term in the equations just might be tearing the universe apart. The local group, the Virgo cluster, the Laniakea supercluster, they were all built atom by atom, galaxy by galaxy. They took billions of years of slow and steady movement to reach their current stunning grandeur. While the rest of the universe may be continually getting bigger, and galaxies gently drifting away with the Hubble flow, the galaxies of Laniakea should always have been able to call it home, until dark energy finally tipped the balance. 5 billion years ago, the expansion of the universe diluted all its matter to a point where a new force could emerge triumphant. That force was always there, waiting in the shadows, part of the very fabric of space-time. But it was weak, and so it sat in the background, content to let the forces of radiation and matter dominate the evolution of the cosmos, until its time finally came. We do not understand what dark energy is, we merely know what it's doing. It's causing the expansion of the universe to accelerate, and its influence is only growing. As the universe expands, its matter contents get more and more spread out, but that same expansion creates more dark energy. Whatever it is, it appears to be related to the vacuum energy of space-time. If you have a completely empty box, devoid of all matter and radiation, you are left with nothing but vacuum. But quantum mechanics tells us that the vacuum is alive, a roiling, bubbling sea of fundamental particles constantly vibrating in and out of existence, imbuing the vacuum with a fundamental energy all its own. Dark energy appears to be a manifestation of that vacuum energy. As the universe expands, there's more empty space, more vacuum, and so more dark energy. 5 billion years ago was the turnover point, when the density of matter dropped for the first time below the density of dark energy. And since then, it's only gotten worse. At the present epoch, dark energy accounts for roughly 70% of all the contents of the universe. In the future, it will be 90%, then 99%, then more, building up on itself as the universe continues to expand. And as that expansion accelerates, it only drives the creation of more dark energy, a process that has no apparent end and shows no signs of slowing down. Dark energy will not let the universe come to rest, and it has already begun its process of deconstruction in the voids. The voids are, by definition, almost entirely empty of matter, only the occasional thin filament of ionized gas or small dwarf galaxy. They are almost entirely pure vacuum, which means they are filled with dark energy and driven to expand by the repulsive effects of that dark force. The voids are the precise locations within the universe where the accelerated expansion takes place. As time goes on, the voids will only get bigger and merge, driving the galaxies at their edges away from each other faster than their gravitational attraction can keep them together. The only objects that will survive the growing darkness will be those that are already gravitationally bound. That means that our local group will survive, although transformed as its individual member galaxies coalesce. And it means that clusters like Virgo will also survive, safe harbors for the thousands of galaxies that already call it home. But the superclusters will not make it. Laniakea, Shapley, and all the millions of others that twist and wind their way to create the backbone of the cosmic web will not maintain their cohesion. It is too late. They have not had time to pull themselves close enough together before the forces of dark energy began their work 5 billion years ago. And finally, we will never complete our journey. The Milky Way will continue on its tragic course with Andromeda, but the local group will never make it to the safe shores of the Virgo cluster, let alone the Great Attractor or whatever lies beyond. Billions of years from now, our passage through space towards the Great Attractor will slow down, stop and reverse. Over the course of hundreds of billions of years, we will see those distant clusters and galaxies dim and fade from view, eventually slipping over our cosmological horizon, caught up in the accelerated expansion driven by dark energy. After long enough time, trillions of years from now, the mega-galaxy that was once the local group will be isolated adrift in a sea of nothingness as every other galaxy slips away. But even then, our motion will not cease. Gravitational interactions within the future galaxy will cause stars to randomly scatter away, and once they slip outside its embrace, they will too be caught up in the accelerated expansion, flung away as if they were never there. One by one, star by star, our galaxy will diminish. The same fate will apply to every macroscopic object. Hundreds of trillions of years from now, each individual body, whether the dead remnants of a star or the frozen husk of a planet, will be completely and utterly isolated from everything else in the universe, separated by vast gulfs of faster-than-light expansion. And with nothing left in the wider universe, with no outside frames of reference, with no stars to gauge motion against or Hubble flows to compare to, with no other sources of attraction or repulsion, only the dim bath of the cosmic microwave background to keep company the universe. What's left of it will finally come to rest.